For more than 100 years, Einstein's cosmological ideas have shaped how humanity understands the universe. They survived every test we could throw at them until a new generation of observations forced us to look deeper than ever before. Space and time were no longer separate. Gravity became geometry. The expansion of the cosmos followed clear mathematical rules. The story worked so well that it became the foundation of modern cosmology. And then the James Webb Space Telescope began sending back answers we didn't expect. This is not about one strange object or one dramatic headline. It is about a growing realization that observations of the early universe are no longer sitting comfortably inside Einstein's cosmological framework. Not breaking it outright, but stretching it in ways that are becoming harder to ignore. Recent discoveries have revealed galaxies that appear far too large, far too structured, and far too mature at a time when the universe should have been young, violent, and disordered. Measurements of how fast the universe is expanding now disagree depending on where and how we look. Even the mysterious force believed to drive cosmic acceleration is showing signs that it may not behave the same across cosmic history. Individually, none of this would be alarming. Science is built to absorb small tensions, but taken together, these findings point toward a far more unsettling possibility. What if the issue is not missing data or imperfect measurements, but the fact that our interpretation of cosmic expansion, time, and large-scale structure is incomplete? This is what makes the moment so profound. Einstein's equations still work. They remain extraordinarily accurate. But history shows that even the most successful theories can describe reality only within a certain domain. When observations begin to push beyond that domain, the result is never a small adjustment. It is a shift in perspective. If that is what is happening now, then we may be witnessing one of the most important turning points in the history of cosmology. Not the collapse of Einstein's ideas, but the beginning of something deeper, stranger, and far more unsettling. If Einstein's cosmological framework is being stretched, it is because James Webb is showing us a universe that does not look the way it is supposed to. According to everything we believed, the early universe should have been a violent and chaotic place. Matter had only just begun to clump together. Galaxies were expected to be small, irregular, and unstable, cosmic infants still struggling to take shape. That expectation was not arbitrary. It was built from decades of theory, simulation, and observation. Large, well-organized galaxies were thought to require billions of years to assemble through slow mergers and gradual growth. In the early universe, there simply hadn't been enough time. James Webb changed that assumption. When astronomers began analyzing deep-field observations, they were confronted with something profoundly unexpected. Instead of a universe filled with primitive structures, Webb revealed galaxies that were already massive, ordered, and mature at astonishingly early times. Some were several times larger than models predicted. Others showed clear rotational motion, organized disks, and chemical complexity that should not yet exist. These were not half-formed objects. They looked settled, calm, established. One discovery in particular captured the attention of the entire field. A colossal, rotating disk galaxy, later nicknamed the Big Wheel, was found existing within the first 2 billion years after the Big Bang. By that point in cosmic history, such a structure should have been impossible. It was not alone. As Webb continued observing, more early galaxies emerged that shared the same troubling characteristics. Too big, too massive, too evolved. Each one strained the limits of existing models. Together, they forced an uncomfortable realization. Either galaxies formed far faster than we understand, or our understanding of the early universe itself is fundamentally flawed. This is where the tension becomes unavoidable. If massive galaxies existed this early, then either matter behaves very differently under primordial conditions, or the timeline we use to describe cosmic history is wrong. That question cuts deeper than galaxy formation, because the age of galaxies is tied directly to the age of the universe, and the age of the universe is tied directly to how fast space has been expanding. If that expansion history is even slightly off, then every cosmic clock we rely on begins to drift. What James Webb is showing us is not just a collection of strange galaxies, it is a warning. a warning that the early universe may not have been as young as we think. And if that is true, then the problem is not with the galaxies. The problem is with our picture of time, expansion, and the story we tell ourselves about how the universe grew up. That realization sets the stage for an even deeper mystery, one that strikes at the very idea of cosmic expansion itself. The tension created by the early universe does not end with galaxies. It reaches into the very method we use to measure cosmic history itself. For nearly a century, astronomers have relied on a simple but powerful idea. The farther away a galaxy is, the faster it appears to be moving away from us. Measure that relationship carefully enough, and you can determine how fast the universe is expanding, and, by extension, how old it is. For a long time, this picture seemed stable, then precision improved. When scientists measured the expansion rate using relic light from the early universe, they obtained one value. When they measured it using nearby galaxies and exploding stars, they obtained another. Both approaches were refined, repeated, and independently verified. They did not agree. This discrepancy is not subtle. It has survived years of new data, better instruments, and rigorous cross-checks. It cannot be dismissed as error or coincidence. The universe is delivering two incompatible answers to the same question. That creates a serious problem. The expansion rate is not just a number. It sets the scale for cosmic time. It determines how old the universe is and how quickly structure could have formed. This brings the story back to the galaxies revealed by James Webb. Their apparent maturity depends entirely on the expansion history we assume. Alter that history, even slightly, and the timeline of cosmic evolution shifts. What once appeared impossible begins to look merely unexpected. But this adjustment comes with consequences. A universe that does not expand at a single, uniform rate undermines the idea of a universal cosmic clock. Age becomes dependent on how expansion is measured, and possibly on where the measurement is made. This is no longer a technical issue buried in equations. It is a fracture in the conceptual foundation of modern cosmology. No definitive explanation has emerged yet, but the consistency of the mismatch leaves little room for denial. The universe is not behaving randomly. It is behaving consistently, just not in the way our current picture demands. That realization points toward a deeper possibility. The problem may not lie in how fast the universe is expanding, but in the assumption that expansion must be the same everywhere, at all times. Following that thread leads directly to the next unsettling idea, one that places time itself under scrutiny. Once the expansion of the universe stopped agreeing with itself, attention turned to the force believed to control it. Dark energy entered cosmology in the late 1990s as an unexpected solution. Observations showed that cosmic expansion was not slowing under gravity, but accelerating. No known force could explain this behavior, so a new one was introduced, not because it was understood, but because it worked. For years, dark energy behaved politely. It was treated as a constant property of space itself, uniform across the universe and unchanging through time. That assumption allowed cosmologists to build a coherent history of the cosmos, from the Big Bang to the present day. Recent observations have begun to strain that assumption. When scientists compare expansion measurements across different eras, the influence attributed to dark energy does not line up cleanly. Data from the early universe points to one behavior. Measurements from the nearby universe suggest another. The mismatch is subtle, but persistent. This is not a failure of instrumentation. The results come from independent methods, different teams, and entirely separate physical processes. Each new dataset sharpens the tension rather than dissolving it. The implication is deeply unsettling. Dark energy may not be constant. A force assumed to be uniform and timeless may instead evolve. Its strength may change. Its influence may depend on cosmic conditions. And if that is true, then the framework built on top of it becomes unstable. The age of the universe, the rate of structure formation, and the interpretation of distant observations all depend on dark energy behaving in a very specific way. Remove that certainty, and the cosmic narrative loosens. This connects directly back to the expansion disagreement. A changing dark energy offers one possible explanation for why different measurements refuse to converge, but it also raises a deeper concern. Introducing a variable force to fix the problem risks replacing one mystery with a larger one. Cosmology finds itself at a crossroads. Either dark energy exists and behaves in ways that defy our simplest assumptions, or the apparent acceleration of the universe is pointing toward a different underlying cause altogether. Both possibilities are profound, because either way, the universe is telling us that the story we use to describe its expansion is no longer complete. And once that realization settles in, it becomes impossible to ignore an even more radical idea that the effect we call acceleration may not be driven by a force at all, but by something far more fundamental, something tied not to space, but to time itself. As dark energy began to look less certain, cosmologists were forced to confront an uncomfortable possibility. The acceleration of the universe might not be driven by a mysterious force at all. The cause might lie much closer to the foundations of physics. Time. Modern cosmology quietly assumes that time flows uniformly across the universe. 1 second here is the same as 1 second everywhere else. That assumption feels natural, but it is not guaranteed by nature. Even Einstein showed that time can slow down in strong gravity. On small scales, this effect is familiar. Clocks on satellites tick faster than clocks on Earth. Gravity changes time. What if that effect does not disappear on cosmic scales? This question forms the basis of an alternative framework known as timescape cosmology. Instead of introducing dark energy, it re-examines how time behaves across the large-scale structure of the universe. The universe is not evenly filled with matter. It is a vast, cosmic web made of dense regions, galaxies and clusters, separated by enormous voids that contain almost nothing. According to this model, time flows more slowly in dense regions, where gravity is stronger, and faster in the vast emptiness of cosmic voids. The difference is tiny from moment to moment, but over billions of years it becomes enormous. An atomic clock inside a galaxy and an identical clock drifting through a massive void would slowly fall out of sync. Over the lifetime of the universe, the difference could amount to billions of years. This changes everything. From within a galaxy like our own, observations of distant regions would naturally suggest faster expansion. Not because space itself is accelerating uniformly, but because more time has passed in emptier regions of the universe. In this picture, the universe does not share a single age. Cosmic time becomes local. History depends on location. The apparent acceleration that led to dark energy emerges as an illusion created by uneven time flow across the cosmos. This idea is radical, but it is not arbitrary. When tested against real observations, timescape cosmology performs surprisingly well. In some cases, it fits the data as well as, or slightly better than, the standard model, without invoking dark energy at all. The cost of this explanation is philosophical as much as scientific. It requires abandoning the notion of a universal cosmic clock. And once that idea is gone, the universe becomes a far stranger place than we imagined. Because if time itself is fragmented across cosmic structure, then many of our deepest assumptions about age, expansion, and cosmic history must be reconsidered. And that realization prepares us for an even more unsettling discovery. One that hints the universe may have begun with a preferred direction rather than pure chaos. Once time is allowed to flow differently across the universe, a strange consequence follows. Expansion no longer needs a mysterious force to speed it up. The appearance of acceleration can emerge naturally from structure itself. The large-scale universe is dominated by vast cosmic voids. These regions contain very little matter, stretching across tens or even hundreds of millions of light years. Over cosmic time, voids grow larger and more numerous, gradually coming to dominate the volume of the universe. In the timescape picture, these empty regions experience faster time flow. More time passing means more expansion, not locally noticeable, but profound when accumulated over billions of years. From our position inside a dense galaxy, this creates a powerful observational effect. Light traveling to us from distant regions often passes through enormous voids. Because more time has elapsed in those regions, the space between us and the source has stretched more than expected. The object appears to be moving away faster, not because it is accelerating, but because the space it travelled through has expanded more. This distinction matters. In this framework, the universe is not accelerating everywhere at once. Different regions expand at different effective rates, governed by how matter is distributed and how time flows locally. As voids grow and come to dominate the cosmic landscape, their faster expansion increasingly shapes what we observe. Over time, the cumulative effect mimics a universe undergoing global acceleration. This explains why distant supernovae appear dimmer than expected. It explains why expansion measurements depend on where and how they are made, and it offers a natural explanation for why no physical signature of dark energy has ever been detected. The acceleration is not a force, it is a perspective. This idea reframes the past few decades of cosmology. The discovery of acceleration was real, the interpretation may not have been. What we may have detected was not a new component of the universe, but the moment when cosmic voids became dominant enough to shape our measurements. If this is correct, then the universe has been quietly misleading us, not through deception, but through complexity, and that raises a sobering realization. When structure determines how time and expansion are experienced, the universe is no longer statistically uniform in the way we assumed. Location matters. Perspective matters. Cosmology becomes less about a single global history and more about a patchwork of local experiences stitched together by observation. This does not make the universe simpler. It makes it far more unsettling, and it sets the stage for an even stranger clue, one suggesting that the early universe may not have been as directionless as we once believed. After questioning expansion, dark energy, and time itself, cosmology encounters a clue that feels almost unsettlingly simple. Direction. According to the standard picture, the universe should have no preferred orientation. The Big Bang is assumed to have produced a cosmos that is statistically uniform, with no large-scale spin and no global alignment. On the biggest scales, everything should average out. Recent observations suggest otherwise. When astronomers analysed tens of thousands of galaxies observed in deep surveys, an unexpected pattern emerged. Instead of rotating randomly, a surprising number of galaxies appeared to share a preferred direction of spin. This was not a subtle effect buried in noise. The alignment persisted across different data sets, different analysis methods, and different regions of the sky. The probability of such a pattern arising by chance was low. This presents a serious challenge. Large-scale alignment implies memory. It suggests that the early universe may have carried an imprint, a subtle rotation or directional bias, that survived cosmic expansion. Such a feature is difficult to reconcile with a purely chaotic beginning. If the universe began with even a small amount of overall rotation, it would ripple through cosmic history. Structure would form differently. Time evolution could vary subtly across regions. Expansion itself might not be perfectly symmetric. This idea is speculative, but it connects naturally with the growing list of anomalies. A universe with uneven time flow and structure-driven expansion is already less uniform than once believed. A faint global orientation would not be an isolated oddity. Some researchers have taken this idea even further. They have explored models in which the universe formed within a rotating spacetime, inheriting angular momentum from its origin. In these scenarios, cosmic rotation is not an accident, but a consequence. These ideas remain controversial. They are not accepted explanations, but their existence signals something important. When multiple independent observations begin pointing away from perfect uniformity, cosmology is forced to reconsider assumptions that once seemed untouchable. The universe may not be directionless, it may not be timeless, and it may not be governed by a single, simple expansion history. Instead, it may carry subtle structure imprinted at its birth, structure that modern observations are only now beginning to reveal. And if the universe truly began with an imprint this deep, the final question becomes unavoidable. What kind of origin could produce a cosmos like this? Once the possibility of a preferred direction enters the picture, the question of origin becomes impossible to avoid. A universe with memory, structure, and asymmetry demands an explanation that goes beyond a simple, featureless beginning. At the edges of mainstream cosmology, some researchers have begun exploring ideas that were once considered unthinkable. Among them is one of the most radical interpretations ever proposed. The universe itself may have been born inside something else. In certain theoretical models, the conditions at the beginning of our universe resemble the interior of a black hole. Extreme density, extreme curvature, a boundary beyond which information cannot return. In these scenarios, the Big Bang is not the absolute beginning, but a transition. The collapse of matter in another universe could give rise to a new expanding space-time, our own. If that parent system possessed rotation, its angular momentum would not simply vanish. It would be inherited. Subtly, quietly, enough to leave a faint imprint on the large-scale structure of the cosmos. This idea, sometimes called the black hole universe hypothesis, is not a replacement for established cosmology. It is a speculative extension, explored precisely because conventional explanations are under strain. What makes it compelling is not that it is proven, but that it naturally connects several independent anomalies. A universe with a preferred direction, a breakdown of uniform time, an expansion history that depends on structure. In this picture, these are not separate problems, they are consequences of a deeper origin. Such models also offer a new way to think about cosmic beginnings. Instead of asking why the universe began from nothing, the question becomes how space-time transitions occur, and whether universes give rise to other universes. This is not science fiction. It is theoretical physics operating at the edge of what observation can currently test. Most cosmologists remain cautious. Extraordinary claims require extraordinary evidence. No direct proof exists for such an origin. But the very fact that serious scientists are willing to explore these ideas marks a shift. When established frameworks struggle to accommodate observation, exploration expands. The universe is no longer assumed to be simple at its birth. It may be part of a larger, colder, and far more complex reality. And as unsettling as that possibility is, it leads to a final and unavoidable reflection. If the universe is stranger than we imagined, then the true revolution may not be in the cosmos itself, but in how humanity understands its place within it. After tracing the path from early galaxies to expansion, from dark energy to time itself, and finally to questions of cosmic origin, the story returns to a familiar name, not as a target, but as a foundation. Einstein's ideas remain central to everything we have discussed. General relativity is not under threat. It continues to describe gravity, space, and time with extraordinary accuracy. Its predictions have been confirmed again and again, from the bending of light to gravitational waves rippling through space-time. What modern observations are pressing against are not Einstein's equations, but the boundaries of how we apply them to the universe as a whole. Einstein showed that space and time respond to matter and energy. Modern cosmology took that insight and extended it to the largest possible scale, assuming that when averaged over vast distances, the universe could be treated as smooth and uniform. The discoveries emerging now are testing that assumption. Galaxies appear earlier and more evolved than expected. Measurements of cosmic expansion depend on how and where they are made. The influence attributed to dark energy may not behave in a perfectly simple way. Time itself may respond subtly to cosmic structure. None of this contradicts relativity. Instead, it suggests that the universe may be applying Einstein's ideas in ways more intricate than our simplified models assumed. This is how science advances. Newton was not overthrown by Einstein. His laws were revealed as a special case. Classical physics was not discarded by quantum mechanics. It was placed within a deeper framework. Einstein's cosmological ideas may now be approaching a similar moment, not replacement, but refinement. A moment where new observations force theorists to extend existing principles into regimes they were never meant to fully describe on their own. If that is the case, then we are not witnessing the failure of one of humanity's greatest theories. We are witnessing its next chapter. And that realization reframes everything that came before. The universe is not rejecting our understanding, it is challenging us to deepen it, which brings us to the final reflection, because moments like this are rare. They mark the points in history when humanity is invited to see reality more clearly and discovers that clarity comes with humility. When a scientific story reaches this point, it is tempting to look for a final answer, a verdict, a clean resolution that restores certainty. But moments like this rarely end that way. What the universe is offering now is not a conclusion, but an invitation to recognize that our understanding has grown to the point where old simplifications are no longer enough. The cosmos revealed by modern observation is not neatly uniform, not governed by a single clock, and not easily reduced to one story of expansion and age. This does not diminish what came before. Einstein's ideas reshaped reality itself, and they continue to guide every serious attempt to understand the universe. The fact that new data is pressing against the edges of those ideas is not a failure of science. It is proof that science is alive. Humanity has reached this kind of moment before, when Earth lost its place at the center of the cosmos, when time and space merged into space-time, when the universe was revealed to be far older and larger than anyone imagined. Each time, the shift was unsettling. Each time, it expanded our sense of place. What makes this moment different is scale. We are not just refining numbers or correcting details. We are confronting the possibility that cosmic history, time itself, and the interpretation of expansion depend on structure, perspective, and conditions far more complex than our simplest models allowed. The universe may not share a single age. Expansion may not mean the same thing everywhere. The early cosmos may have carried memory, order, and subtle asymmetry. These ideas are still being tested. They may evolve, some may fall away, but the questions will remain, and that is where their power lies. Because science advances not by defending certainty, but by following evidence, even when it leads somewhere uncomfortable. James Webb did not break cosmology. It exposed its growing edge. At that edge stands humanity, doing what it has always done at its best, listening carefully, questioning deeply, and accepting that the universe is under no obligation to match our expectations. This is not the end of the story. It is the moment we realize how much more there is to learn. And in that realization lies something profound. The universe is still revealing itself, and we are still young enough, curious enough, and humble enough to be surprised.